Alright, so in this video I'm just going to show you how to prove that the intersection of any family of convex sets is itself convex. So first, what is a convex set? What does it mean for a set to be convex? So say we have some set S, right? We say that S is convex if and only if for all pairs of points, I don't know, let's call them P1 and P2, where those are in S. Let me get rid of those parentheses. In S, all the points between P1 and P2 are in S, right? So, for example, usually the canonical kind of example of a convex set is like the set of points that are bounded by some polyhedron. So, like, if you have like a circle, then that's convex, because if you draw a line between any 2 points in the set, then it'll also, like, all the points on that line are going to be in the set, right? But if you have like this weird like half donut shape, then this is not convex, because if you draw that line, you can see these points in between those points like are not in the set, right? So how are we going to prove now? Okay, so first, it seems like it's easy to prove this, right? Like if you have an intersection of a bunch of these convex sets, like this region here, like it seems obvious that it's convex, but it's not as trivial as I think it might seem to be. So if we're just gonna prove this mathematically, it kind of makes sense. The way that I'll do it, it seems pretty intuitive, but just, you know, in like a mathematically rigorous way, it's a little bit different than you might just think about proving it visually, which is, you know, because if you want to prove it for higher dimensions, you can't just prove it visually. You know, it kind of stops working after 3 dimensions, right? All right, so let's get into it. So let's say that we have a family of convex sets, right? So let's call that family F, right? And let's just make it a set of sets, right? Let's call them S1, S2, etc., right, through. And let's just say that it's a finite family, right? Maybe infinite can be an exercise to the reader after this is done, or I guess the watcher in this case. And now let's say that you have some. We just want to prove that F is convex now, right? Or really, okay, maybe F is that family of sets. So we wanted to say like that. Let's call I the intersection of all the sets in F, right? So I this is the big intersection symbol. It looks kind of bad, but, you know, whatever. For each set in F, right? So like, let's call it S in big F. This intersection of all sets in F, that's what we're trying to prove is convex, right? So we want to show that I is convex. All right. So now how do we do this? Well, we can just use the definition, right? We just find 2 arbitrary points in I, and prove that they have to obey this convexity property, that any points in between those 2 points are also in I. So let's do that now. So zoom out a little bit, make some more space here, and then I'll just scroll down. So let's take 2 points in I. Again, let's call them P1, P2 in I, right? And so we know that, what do we know about P1 and P2? Well, because they're in the intersection of all these, they're in the intersection of F, right? All the sets in F, right? So P1 and P2, what are they? They're inside S1, they're inside S2, etc. They're in all of these sets, right? So if they're in all of those sets, well, all of those sets are convex, right? That means that the points between P1 and P2 are also in S1 all the way through Sn, right? So all these points also have to be in there. And then from that, I mean, you know that P1, P2 are in I, and because that's the case, or because of the definition of I, that means, you know, as we just saw, P1, like all the points between P1 and P2, right? So I don't know, called points between P1 and P2 are also in I, right? So because this is the case for all arbitrary points P1 and P2, therefore I is itself convex, right? So this is our little proof, you know, QED, whatever. Now, notice we never really defined, like, what does it mean for a point to be between two other points? We're not like, you know, we're just describing this general property of, okay, points are between two other points. And we didn't even need to. We just used the properties of set intersection, basically, and that was pretty much it. So it just goes to show how easy it is with these really minimal ideas of, you know, set inclusion, how easy it is to just prove arbitrary things that maybe you don't even necessarily have like a good intuition about. Even if we didn't have that intuition about convex sets, it's still, this intersection idea allowed us to just understand immediately like what we're doing here. So I thought that was pretty interesting, and that's it for this video.